Okay, we are back, and actually I am giving these lectures one after another. So, I am going to talk to you about a delightful result called the mean value theorem. What does it say? It says that take a function f from a to b, sorry, from ab to r. ab is a closed interval in r. Now, assume that f is continuous on ab. See, continuous on AB actually means at the right and left hand points we are talking about, at the point A we are talking about right continuity, at the point B we are talking about left continuity, because I do not know anything about this function outside the interval A and B. Then assume that f dash, the derivative, exists on the open interval AB. Then I am writing it red, it is so important. Then there exists, this is a sign for there exists, C which is lying in the open interval AB, that is strictly bigger than A and strictly less than B, such that FB minus FA is F dash of C into B minus A, or the way most calculus books write, so what does this signify? Let us look at the picture, the geometry, and that will be enough. So this is f prime C. So this is the way calculus books write, whichever way you, I usually write in this form, or you can take this form, it's up to you. But this form would immediately give you some geometric meaning. Let us just try to see that. So I draw, suppose the function is like this between A and B, a continuous function, nice, of course, nice looking, and it is differentiable at every point. It means derivative simply means that you can draw a tangent line at each point, one unique tangent at each point, one tangent only. So what is my FB minus FA by B minus A? So if you look at the point A, this point, the coordinates of this point are A and FA. The coordinate of this point B and FB, the endpoints. Now let us join these two endpoints AFA and BFB of the graph by a straight line. And if I take this line, if I write it as L, then slope of L is equal to FB minus FA by B minus A. What does it tell you? What does this mean? It tells you, okay, it does not matter, I can have a point C lying between A and B. So this is the point C. So if I draw the tangent at that point, the tangent to the curve at the point CFC, because this point is CFC, tangent to the graph of the curve, graph of the function at the point CFC, that must be parallel to the line segment joining BFB and AFA, and then that means that they have the same slope. But the slope of the tangent line at the point CFC is nothing but f dash C, and that is exactly what it is written. So the geometry gives you the answer. Now the question would come, is this only done for functions which are on some closed interval? It does not tell me anything if I take functions say from R to R. Of course, once you have functions from R to R, you are more flexible. So it does not matter, then you take any 2 points AB on R, then the same story can be told that you can always write f b minus f a by b minus a is equal to some f dash c, where c is strictly lying between a and b, if you assume that the function is continuous and differentiable throughout. Now, let us take one by one the consequences of the mean value theorem. So, let us look at the first consequence. So, let us just keep the definition to f from a b to r, the definition which we have started. Now, let me consider the situation where f is continuously differentiable. It means that f not only has a derivative, but the derivative of f as a function of x is continuous. So, I repeat, a function is continuously differentiable if the derivative of f as a function of x is continuous. So, now I have just told you about continuous differentiable functions. So, let me assume that f is continuously differentiable. So, f dash x is continuous. Now, the interesting feature is the following, that suppose I take the interval a b, closed interval a b, and I say that f dash x is continuous, means it is continuous on the closed interval a b. So, I cannot say just continuous on the open interval a b, of course, it is continuous on the open interval a b if you say continuously differentiable. Let us assume that f is not only differentiable over the open interval a b, let us take that f is differentiable on the closed interval a b, but at the right interval, at the right side you take the left derivative, right derivative at a and the left derivative at b. So, let us go on this thing. So, f dash x is continuous on a b. Now, what does it tell me? Tell me the following fact, that if this is true, if f dash x is a continuous function, then if I maximize this function, maximize or minimize does not matter, because a b is a closed interval, this is a finite number alpha, this bound exists, or maybe it is better to say capital M because it is maximum. So, this value is finite. So, what is the consequence of this now? The consequence is the following. Now, at the two endpoints I apply the mean value theorem to get the following, f b minus f a by b minus a is equal to f dash c for some c in a b. Now, whatever be your f dash c does not matter, it has to be less than m. So, f b minus f a is b minus a is less than equal to m. So, f b minus f a is less than equal to m times b minus a. Now, let us see what happens. So, you have got this fact. Now, if I swap b with a, I am changing b with a, what sort of inequality will I get? So, now I make a swap, right. So, if I change the inequality, then I can get a reverse inequality, that this is greater than minus m times b minus a. So, let me tell you how. Now, you have got this. So, but you also know that because of our studies about continuous function that the minimum value of this f dash x over x minus a b, this value also exists. So, this is m, but f dash c is then greater than equal to m because m is the minimum value. So, I can again have this now. This simply means the following. Let us see what does it mean. It means that no, f dash c is here greater than equal to m. So, what would happen is that we will write now, how do I get this? So, f b minus f a by b minus a greater than equal to m. So, you get f b minus f a is greater than equal to m times b minus a. So, this is a fact that you can get immediately from the mean value theorem, but what does it tell? It does not tell me anything more. The fact is again this. Now, if I now take, if you have f b minus f a by b minus a, you can write this as f dash c. Let me take the modulus of this quantity. If you take the modulus of this quantity, this implies mod of f b minus mod of f a is equal to f dash c into mod of b minus a. But again, because f dash c is bounded, f dash x is bounded, mod of f dash x is bounded. The absolute value also must be bounded, it cannot blow up. So, the absolute value also has some maximum value. So, bounded actually means that because the derivative is bounded, so f dash x is less than some capital L. So, let f dash x is less than equal to some capital L for all x element of a b, and this implies the following. This implies that f b minus f a is less than equal to L times b minus a. Now, it does not matter whatever x and y you choose between b and a. So, you take any x and y between b and a, I can always show that f x minus f y is less than equal to L, the same L, x minus y. So, this simply means that this property is called the Lipschitz property. So, we say that f is Lipschitz, and this is a very important property in many aspects of mathematics and engineering sciences, economics and all those things. So, f is Lipschitz over a b with Lipschitz rank L. A very unlikely function which satisfies the Lipschitzianness over any given interval is a sine function. It is very unlikely. So, for example, you take the sine function so take any a strictly less than b, and you can write sine a minus sine b by b minus a is equal to cos of, so I am applying the mean value theorem, cos of some c where c is lying between strictly between b and a. But so again you can write mod of sine a minus mod of sine b is, because cos of c is always less than 1, is less than equal to mod of b minus a. So, with Lipschitz rank L equal to 1, the sine function is Lipschitz in the interval a to b. Now, a very simple application of this is the Rolle's theorem, which usually is taught in calculus classes before the mean value theorem, but I decided that we should go from the mean value theorem to the Rolle's theorem, and it makes life obvious. Some people say, okay, no, you should do Rolle's theorem first because Rolle's theorem is used to prove the mean value theorem, but does not matter, you can always prove the mean value theorem without the Rolle's theorem. Let us look at Rolle's theorem. Rolle's was a very colorful character, by the way, but this theorem is very interesting. Same sort of stories. Now, write down the mean value theorem. Now, make this interesting assumption. The assumption is, let FB is equal to FA. So, if you assume that FB is equal to FA, then you are showing the following, that then F dash C is equal to 0, which means if this is holding, so if FB is equal to FA, there exists C which is in the open interval a to b such that f dash c is equal to 0, which means I can find the critical point of the function between lying strictly between a and b. For example, if you look at this diagram to explaining the Rolle's theorem. So, this is a and this is b, their functional heights are same, so it is like this for example. Then you see there is always one point here where the tangent is parallel to the x axis, and that is exactly the meaning of f dash x equal to 0, which we had not told about in the last lecture. The tangent parallel to the x axis means that it has a 0 angle with the x axis, and hence the slope value is 0, because that the tangent value is the tangent of the slope of the tangent is actually tan of the angle at which it intersects the x axis, which is a very well known fact. So, here is your C. So, you see how interesting result of the mean value theorem leads you to several more facts. There are certain things, there are more things you can talk about. Now, I will tell you something interesting. Suppose f dash x is 0 throughout the interval a b, then what is going to happen? So, use the mean value theorem to show that if f dash x is equal to 0 for all x in a b, then f is constant on a b. I would leave you to work on this, it is just fun. So, how by simple arguments you can get fantastic ideas about the nature of functions. So, with this let me stop, and in the next talk we are going to talk about a very important thing. If I want to compute a function which is slightly difficult, like if I tell you compute sine 3 degrees, you can't immediately give me the answer. So, is there any way to compute them, these sort of difficult functions, by just doing basic arithmetic operations of addition, subtraction, multiplication and division? The answer amazingly is yes, we can do a very good approximation, and we will talk about that in the next class on Taylor's expansion. Thank you very much.